Today, we are diving into a quantum algorithm that honestly feels a little bit like magic. It's this wild story about a brilliant idea from the 90s that's found a totally unexpected and frankly super important new mission in the messy world of today's quantum computers. So yeah, let's get right into it. Okay, so first, a question for you. Imagine there's a secret password, right? A long string of ones and zeros, and it's hidden deep inside a computer. How would you figure out the entire password perfectly in just one single guess? I mean, it sounds impossible, doesn't it? Well, guess what? That is the exact puzzle we're going to solve today. So to really appreciate just how hard this is, let's start with the way our everyday computers, classical computers, would try to solve this problem. Let's just think of it like a game. You've got a black box, some people call it an oracle, and it holds a secret code made of ones and zeros. The only thing you can do is give it an input, and it spits about just a single bit of information that's based on that secret code inside. Now, the most obvious way to win this game is to just be methodical, right? You'd ask, hey, what's the first bit? And then you get the answer. Okay, cool. What's the second bit? And so on, one by one, all the way down the line, until you have painstakingly put the whole thing together. So here's the bottom line. For a secret code that is n bits long, you have to ask that oracle n separate times. If the code is 100 bits long, that's 100 questions. It gets the job done, sure, but it's kind of like a brute force attack. But what if there was a shortcut? What if there was a way to ask just one really clever question that revealed the entire secret code all at once? Well, this is where quantum computing completely changes the rules of the game. And that brings us to the hero of our story, the Bernstein-Vazirani algorithm. It was developed way back in 1992 by Ethan Bernstein and Umesh Vazirani, and it was designed to solve this exact problem, to find that hidden binary string, which they call S, that's locked away inside that black box. And how many times does this quantum algorithm need to ask the oracle to find the entire n-bit string? Get this, just once. That's it. One single query to this quantum oracle, and boom, the whole secret code is revealed. And this just lays it out so perfectly. Over here on the left, you've got our classical computer, just plugging away, needing n questions for an n-bit string. But over on the right, the quantum computer, using this Bernstein-Vazirani algorithm, gets the whole shebang in a single shot. This isn't just a little faster, it's an absolutely massive speed up and a beautiful demonstration of quantum power. Now that sounds amazing, right? A flawless victory for quantum computing. But here's where our story takes a sharp turn. We're about to leave the clean, perfect world of theory and enter the much, much messier world of real-life hardware. You see, the quantum computers we have right now are what experts call NISQ devices. That stands for Noisy Intermediate Scale Quantum. And the keyword there, you guessed it, is noisy. They're incredibly powerful, but they're also unbelievably delicate and really prone to errors from the world around them. This quantum noise is, well, it's kind of like static on an old radio. It's interference from everything, tiny vibrations, changes in temperature, even stray magnetic fields. All of this stuff can mess with the delicate quantum states while a calculation is happening. It can flip bits around, scramble the final measurement, and basically turn what should have been the perfect right answer into something totally wrong. So that beautiful, perfect, one-shot answer from our amazing algorithm, noise can just shatter it. Instead of getting the exact secret code, you might just get a random jumble of bits. The magic trick completely fails. And this noise problem, it's one of the single biggest hurdles in quantum computing today. But here's the really cool part. This very problem, this issue of noise, has given our 30-year-old algorithm a brand new, incredibly important job. It's gone from being this cool, theoretical example to a vital, practical tool that we need right now. So scientists are developing these really clever software tricks to clean up all that quantum static. They're called quantum error mitigation, or QEM for short. Honestly, the best way to think of it is like noise-canceling headphones, but for quantum computers. These are software techniques that run after the calculation is done, and they try to correct for the errors that were caused by all that noise. So to actually build and test these error mitigation techniques, you need a perfect benchmark, right? You need an algorithm whose correct answer is so simple and so predictable that you can tell in an instant if your noise cancellation is actually working. And it turns out Bernstein-Vazirani is the absolute perfect candidate.
This quote actually comes from some research that was testing a specific error mitigation method called fuzzy C-means, and our algorithm was totally the star of the show.
And just look at these results. This chart shows the accuracy of the algorithm's output. The noisy, uncorrected result, that first bar, it's only right about 85% of the time. But then, when you apply these error mitigation techniques, like the ones from IBM or this fuzzy C-means method, look at that jump. The accuracy skyrockets to nearly 99%. The noise is basically erased.
So why is it such a perfect test case? Well, because in a perfect, noiseless world, the Bernstein-Vazirani algorithm always gives you a single, sharp answer. Scientists call it a delta function output. There is zero ambiguity. So any result that isn't that one perfect answer is 100% because of noise. And that makes it the ultimate measuring stick for figuring out how well your error correction software is working. So, wow, we've really been on quite a journey here, haven't we? We've gone from a mind-bending theoretical idea all the way to a practical, hands-on tool for building the future of computing. Okay, so let's just quickly recap the big takeaways here. First, Bernstein-Vazirani is just a classic, awesome example of quantum advantage. It solves a problem in one step that takes a regular computer many, many steps. Second, we know that real-world quantum computers are noisy, and that noise just wrecks these perfect results. But third, and this is the really cool part, that very problem has given our old algorithm a brand new purpose. It's now the perfect testbed for building the error mitigation software that's going to make future quantum computers reliable and truly powerful. You know, the story of Bernstein-Vazirani is such a great reminder of how even abstract, theoretical ideas can become essential tools in ways no one ever expected. It really makes you wonder, as we get better and better at taming this quantum noise, what other seemingly magical algorithms are just waiting out there to help us solve problems we haven't even dreamed of yet?